In this video, I'm going to continue our discussion of conjugated systems. And in particular, we're going to be talking about what are called pericyclic reactions, which are reactions that are used with these conjugated systems. The one we'll be looking at today and in the next few videos are what are called cycloaddition or Diels-Alder reactions, where we will be losing 2 pi bonds and gaining 2 sigma bonds. In future videos, we'll talk about electrocyclic, which are intramolecular ring closures, where you lose 1 pi bond and gain 1 sigma bond. So you're essentially converting a pi bond to a sigma bond at some point in the molecule. In future videos, we'll also be talking about what are called sigmatropic reactions, which are rearrangement reactions in these conjugated systems. So there is no net loss or gain of bonds. Something that all of these pericyclic reactions have in common is that the catalyst or solvents do not affect the rate. They all go under either heat or light conditions. They are very stereospecific, which we'll talk a bit more about in the next video, and there are no ions or radicals as intermediates. So this is just all about the molecular orbital overlap. So the cycloaddition we'll be looking at today is what's called the 4+2 cycloaddition. That's because the diene has 4 pi electrons, where the dienophyl has 2 pi electrons. And so this is then doing an addition, so we're bringing 2 of these things together to turn it into 1 molecule. What we have shown here is our diene, which is the electron-rich molecule, and our dienophyl, which is electron-poor. And so we're going to end up bonding both of these things together to make our product here. And so this isn't the way that it's actually happening, but a good bookkeeping method for doing this is to do the arrow pushing. So we can have this come over here. So that pi bond will be coming to form a sigma bond. This pi bond will be coming to form another sigma bond down here. Then this pi bond is moving over to here. So we end up with that pi bond right here. The sigma bonds that we are generating are this one right here and this one right here. Again, that's not how it's actually happening, but it's sort of a good bookkeeping method that a lot of students find helpful when doing these types of reactions. And you'll notice that this is done under heat conditions for this particular 4+2 cycloaddition, and what we end up with is the 1,4 product. So this substituent is on the 1 carbon, this one on the 4 carbon, or it could be the reverse of that depending on what those substituents are, but they are 1 and 4 away from each other. We can also do this when we have an alkyne, so that would be our dienophyl with the alkyne right here, where again this is going to come over here, this comes over here, will form that sigma bond, this pi bond moves over there, and so we end up with that pi bond right there, and we still have a pi bond right here because we are only using one of the pi bonds here in our alkyne. And so you may be wondering what this D and what this W are right here. So the W just stands for electron withdrawing group, and so those would be things like this carbonyl or this cyano group, and these pull electron density away from the dienophyl. So remember, the dienophyl is the electron poor, so by making it even more electron poor, it makes it more reactive. Similarly, the D here stands for electron donating group. These can be things like alcohols and ethers, or these amine groups. These add electron density to the diene. Remember, the diene is electron rich, so adding more electron density to it will make it even more reactive. And so what that looks like is this. We can think about it in terms of the resonance. So our electron donating group is going to take one of these lone pairs, bring it down here, and then this pi electrons will go over here to form a lone pair that's negatively charged right there. And then with the electron withdrawing groups, we can see that these pi electrons can move over here, then these ones over here, and so that will form a positive charge right here. So we get a carbocation right there. And so you can also see that the negative from this carboanion right here and this positive from the carbocation right there will cause those to be attracted to each other. So this is why it ends up making the 1,4 product here, because these two are going to orient towards each other right here. And so that's where we're going to end up with that 1,4 product. And that is the case when our electron donating group is on the 2nd carbon in our diene. But if it's on the 1st carbon in our diene, then we get something that looks more like this, where now the electrons that are being donated donated are coming from right here, so they move down there, then these move over to right there, and then these move up to right there, so that we end up with our negative charge right there. That's going to be oriented towards the carbocation right there, and so we will end up with the 1,2 product if our electron donating group is on the first carbon rather than on the second carbon in our diene. And this is just our reaction energy diagram right here. So we see we have our reactants on the left, that's our diene right here, and our dienophile right there. When we have the transition state, we have these partial sigma bonds right here in blue. We are then going to be forming this pi bond right there in blue. These ones in red are all the bonds that are being broken. Then we end up with our product, which in this case would just be this cyclohexene, and that is lower in energy, so this tends to be an exothermic reaction. We can look at a few examples of this. So we have this with our diene on the left and our dienophile on the right. So again, we have these electrons moving there to form that sigma bond, these ones coming down here to form that sigma bond, these ones moving over here to form that pi bond. So this is the pi bond we're forming right there, and we end up with this as the product. We have a few more examples right here, which comes from the textbook that I'm using, which is the Organic Chemistry textbook by L.D. Wade. So again, what we see is we can have the electrons here coming to form a sigma bond there, these ones coming to form the sigma bond there, this moving over here to form that new pi bond. We have our electron withdrawing group right there, and so we end up with this as the product. And then we can do this again with the alkynes. So this is the alkyne, so we still end up with that double bond right there in the product. And then this one right here has the electron donating group on it, and so it has 2 electron withdrawing groups, so the orientation will not actually matter on this one. We end up with the double bond right there. This is the single bond we're forming and the single bond we're forming. And we see that the stereochemistry is shown on here. We'll talk more in the next video about how to determine the stereochemistry on the products for these. As I said before, these reactions are done through the molecular orbital overlap, so we want to be able to look at these using the molecular orbitals. So these are the molecular orbitals for the diene, which is the electron rich, and the dienophile, which is the electron poor. And so we see in the diene, we have in our bonding orbitals down here, we have the filled electrons, and then we also have in our dienophile, we have this up here, which is the lowest unoccupied molecular orbital. So we're going to want molecular orbital overlap between the highest occupied molecular orbital of our diene and the lowest unoccupied molecular orbital of our dienophile. And so what that looks like is this. If we are looking at it using just heat, then the diene is in the ground state, and so both of the electrons here are in the pi2 bonding orbital, and we see that we end up with constructive overlap. So remember, the colors on these orbitals here, so the green on this one, the green on this one are telling us about the phase of these orbitals. Then we have the brown on this one and the brown on this one. So we need those to be the same color in order for there to be overlap. And so we see that when we are in the ground state for the diene, that these have constructive overlap. Whereas if we are in light conditions, then we will end up promoting one of the electrons into the pi*3 antibonding orbital on our diene, and so we will end up with one of these being out of phase. And so that's why this will not actually react in these light conditions. You need it in the heat conditions in order for the diene and the dienophile to react with each other. But if we look at this using something like this 1,3,5 hexatriene, where now we have all these molecular orbitals. So now we have these as our filled molecular orbitals, where up here is our highest occupied molecular orbital, then up here is our unfilled anti-bonding molecular orbitals. What we end up seeing if we are trying to do this reaction is we bring in our dienophile here, which is just this ethene, then our diene, which is this 1,3,5 hexatriene. We are going to react those, and we end up with this 1,3 cyclooctene right here. here. But in this one, if we look at the molecular orbital overlap, now if the 1,3,5 hexatriene is in the ground state, we end up with destructive interference here with these molecular orbital overlaps. But if we then go in the light conditions, where we promote one of the electrons up into the pi4 star antibonding molecular orbital, now we have all constructive interference between these molecular orbitals. And so if we want to do the 1,3,5 hexatriene Diels-Alder reaction, then we actually have to do this in light conditions rather than heat conditions. And what we will find in general is that if we have an even number of bonds in a conjugated system, then we have to do that in heat conditions, whereas if we have an odd number, then we have to do this in light conditions. So our diene was an even number, it had 2 double bonds in the conjugated system, and so that's the one that we needed the heat conditions for, where the 1,3,5 hexatriene has an odd number, it has 3 pi bonds, and so we needed the light conditions in order for that one to proceed. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.